Welcome guys to the new lecture which is about buckling of columns. There will be various topics inside this lecture which need to understand so that we can completely able to understand the behavior of columns in buckling. Please keep in mind that not only a member should satisfy the strength and deflection requirements, but it must also satisfy the stability requirements, right? Stability is particularly important if the member is long and slender. So if it is not long, if it is short and it is not a cylinder and it supports a compressive loading that becomes large enough to cause the member to suddenly deflect laterally or sideway, right? So in these scenarios when it is long, slender and uh, uh, the loading is large enough so that it can deflect laterally or sideway. So in this case, stability becomes more important, and vice versa. If it is not long, not cylinder, load is not that large enough, so the concern about stability is not that much. These members are called columns, and the lateral deflection that occurs is called buckling. Okay, so this is your column because it is long, it is slender, and it is subjected to some load, and the shape, the deformed shape, this shape is called, this deflection is called buckling of column, right? And it happens because of this excess axial load. Quite often the buckling of a column can lead to a sudden and dramatic failure of a structure or mechanism, and as a result special attention must be given to the design of columns so that they can safely support their intended loadings without buckling. Okay, so what is that load that it need to safely support? Basically, this is the question, right? The maximum axial load that a column can support when it is on the verge of buckling is called the critical load. So uh, this is a column and you have applied some load through its center or centroid, right, or center of gravity, and you are keep on increasing this load. P is keep on increasing, and at some point when you reach the P critical, this is the last point at which the column will be in stable equilibrium, and if you increases the load beyond that point, the column will not be in stable equilibrium and it will shift to unstable equilibrium. So stability is the requirement, and we need to know the various parameters on which it depends, right? We can study the nature of this instability by considering the two-bar mechanism consisting of weightless rigid bars that are pin connected as shown in figure 2. So this is your figure 2 and this is A part. So these are two members, right, connected at point A. Both are pin jointed at both the ends. This bar is pin jointed at its supports, also the other one, and at this pin or this center point or this middle point a spring is attached to it, right, in this direction. Now the length of each bar is L by 2. When the load is increased, the bar tends to bend in this direction, right, either inward or outward, but here we are considering it is moving inward and compressing the spring. So spring is offering some force, some push force to it, right? The angle that it is making with its is original vertical position. This is the line of its original vertical position. The angle is theta, right? This is hypotenuse, this is perpendicular, and this is base. So you know very well that this perpendicular is equal to sine theta into hypotenuse, right? So you can easily find it out. Also, if you can invert it, this is the invert form of this triangle and this is the invert form of this triangle, right? And this perpendicular is shown here, and perpendicular is equal to p tangent theta, you know very well, right? Now this f is equal to 2 times p tangent theta. Please keep in mind these terminologies. Okay, now when the bars are in the vertical position, the spring have a stiffness K is unstretched. As I told you, a small vertical force is applied at the top of one of the bar. Here you have applied small vertical force P, and to upset this equilibrium position, the pin at A is displaced by a small amount delta. Okay, so this equilibrium position is disturbed and the spring has been moved or compressed by an amount delta, right? As shown on the free body diagram of the pin, figure 2c, here you can see the spring will produce a restoring force F, which is equal to K times delta. So if you consider this F, which is produced in this spring, it is equal to this K times this delta, because this delta is the displacement and K is the stiffness of the spring, right? So stiffness force is always equal to the displacement multiplied by stiffness, right? So F is equal to K times delta in order to resist the two horizontal components Px, right? So in order to resist this Px, which is equal to P tangent theta, uh, F should be equal to K times delta, which tend to push the pin, right? Since theta is small, therefore the delta is almost equal to theta into L by 2 and not sine theta L by 2, and tangent theta is almost equal to theta, right? Because theta is very small here. Thus, the restoring spring force becomes F is equal to K theta into L by 2. Now, in this equation, F is equal to K delta. You have just replaced this delta by its value, which is equal to theta into L by 2. So, the equation becomes F is equal to K theta L by 2, and the disturbing force is 2px is equal to 2p theta, right? If the restoring force is greater than the disturbing force, if the force in the spring, the restoring force, that is spring force, right, it is greater than the disturbing force, the external force, that is K theta L by 2, this K theta L by 2 is greater than this 2p theta, then noticing that theta cancels out, since this theta will cancel out with this theta, and this 2 will go to the denominator, and it will be KL by 4, just like here. So P will be less than KL by 4. So this was the condition when the restoring force was greater than the disturbing force. So this is the equation of stable equilibrium, and vice versa. What happens if the restoring force is less than disturbing force? Then this sign will be opposite. K theta L by 2 will be less than 2p theta, right? And then again theta will cancel out and P will be greater than KL by 4, right? So this is a condition for stable equilibrium, since the force developed by the spring would be adequate to restore the bars back to their vertical position, right? However, just as I explained, if reverse happens, then P will be greater than KL by 4, and this will be the condition of unstable equilibrium. Then the bars will be in unstable equilibrium. So basically KL by 4 is a criteria. Now we will talk about this criteria. In other words, if this load is applied, which load? KL by 4, and a slight displacement occurs at A, as you know this is A, right? The bars will tend to move out of equilibrium and not be restored to their original position. So the bars will be in unstable equilibrium and will never come back to their original position. The intermediate value of P, which requires KL theta by 2, is equal to, because till now we have discussed either greater than or less than, right? So if what happens if it is equal to that, so in that case this is called the critical load, because in this condition the neutral equilibrium will be there. The springs will remain in this position and will not deform further, or will not restore to their original position unless and until P critical is there. So P critical is that load at which the deformed shape will continue or will remain there. It will not restore its position, and it will not further deform and reach to instability, right? Instability. This loading represents a case of the bars being in neutral equilibrium, since P critical is independent of the displacement theta of the bar. See, there is no value of theta in this equation. Any slight disturbance given to the mechanism will not cause it to move further out of equilibrium, nor will it be restored to its original position. So instead, the bars will simply remain in the deflected position, as I explained. So the figure 3 is basically showing you this point. What is this line? This line is the neutral equilibrium. This is the point of critical load. If your load is less than this critical load, the column will be in stable equilibrium, and if it exceeds your critical load, then the column will be in unstable equilibrium. Okay. So this point is called bifurcation point or critical point or equilibrium, neutral equilibrium point, right? You can read it by yourself. The second topic regarding this is now critical buckling load, because still now we have discussed about the critical load, right? Now we will take some assumptions. The assumptions are that the column to be considered is an ideal column. Okay, and what does an ideal column means? Meaning it is made of homogeneous linear elastic material. Three assumptions are here: homogeneous, linear, elastic material, and it is perfectly straight before loading. So before loading it is perfectly straight, right? Here the load is applied through the centroid of the cross section, and the load is perfectly applied at its centroid, and it's transferred through it to the centroid, right? Now what happens? Okay, you can go through these slides and read it by yourself, and I will explain you here. When you apply the load P, right, and you keep on increasing it, right, and you just reach the P critical point. Now at this P critical point, if you applied a lateral force at its center, middle of the column, F, a very small force, and it causes buckling in it, right? Now if the column is at P critical, if you remove this force F, the column will remain in this position no matter how long it takes. Okay, it, as long as the load is P critical, either it is not increasing nor decrease, either it is not increasing nor decreasing, the column position will not change, right? It will remain in this position. Now what happens if you reduce the load? If it is less than, if you make the load smaller than the P critical at this point, for example, you have applied P critical of 50 kPa here, right, and the column continues to be in this shape. Now just make it 45 instead of 50. So instead of 50 kPa you make it for 45 kPa, and the column will start coming to its original position. And if you reduce it to 0, it will become straight column just like the previous one, right? What happens if you increase from the P critical? At P critical there were 50 kPa, right? And what if you increase it to 55, or let's say 60 kPa? So it will start deforming it and the buckling will increase. So this is basically the concept and the criteria. Okay, so you just go through this text and read it by yourself. The critical load for the column is given as P critical is equal to pi square EI by L square, and this equation is referred to as Euler's formula. Okay, this load is called Euler load because it was firstly suggested by Swiss mathematician Leonhard Euler. So this is your equation that you need to understand, that your P critical is inversely proportional to length of the column. As the length of the column increases, your P critical decreases. So for everything same, if there are two columns, one with 10 feet height and one with 15 feet height, the values of 10 will be divided by 100 and of 15 has to be divided by 225. So your load will increase drastically. Okay, so as noted above, the critical load depends on material stiffness or elastic modulus, just like this, your moment of inertia. So this is material property E, this is your geometric property, cross-sectional property. So if the cross-section is larger, P critical will be larger, and vice versa with the length, right? Therefore, a column made of high strength steel offers no advantage over one made of lower strength steel because the modulus of elasticity is same. So yield stress doesn't make any difference. For grade 40, grade 60, grade 80, it remains same as long as the modulus of elasticity is same. Also note that P critical will increase as the moment of inertia of cross section increase because both are directly proportional, right? Thus, efficient columns are designed so that most of the column's cross-sectional area is located as far away as possible from the center of the section. So that's why efficient columns are designed, and hollow sections such as tubes are more economical than solid sections. Why? Because they are better sections than the rectangular and solid, which are built up from channels, angles, plates, etc., right? Because their moment of inertia is large as compared to the solid sections and regular sections. Now, since P critical is directly related to I, a column will buckle about the principal axis of the cross section having the least moment of inertia. Now, this is the column with two directions. One is larger and other one is smaller. Now, this column will always bend in this direction about A axis in the B direction, right? Why? Because its moment of inertia in A direction is much larger than what in the B direction. Therefore, it will buckle always in this direction. So a column having a rectangular cross section like a meter stick, this figure 5, will buckle about AA axis, not the BB axis. It will always buckle about this AA axis, right? Because of this, engineers usually try to achieve a balance, keeping the moments of inertia the same in all directions. That's why engineers usually prefer the uh, square or rectangular columns where the difference is not that much between the two orthogonal directions or the dimensions. Uh, Geometrically, then circular tubes make excellent columns, right? If you are talking about geometric, then circular tubes are the excellent columns. Square tubes or those shapes having Ix equal to Iy are also often selected for columns, right? So your main objective is that to make them equal or as close as possible. To summarize, the buckling equation for a pin supported long cylinder column is, now you have seen this word first time, pin supported, because in our next section of the lecture we will be talking about the support conditions. So as of now, don't worry about the pin supported or fixed supported. So for the pin supported, the way the formula is P critical is equal to pi square EI by L square, which is your Euler's formula, right? What is P critical is your critical axial load at which the column begins to buckle. This load must not cause the stress in the column to exceed the proportional limit. Okay. E is elastic modulus, I is moment of inertia, and L is unsupported length. Now, what is this unsupported length? It is also going to be in our next section of this topic. So, for design purposes, the buckling equation can also be written in terms of stress by using moment of inertia is equal to A into R square. What is R? R is the radius of gyration, right? And A is the cross-sectional area. So we have P critical is equal to pi square E I by L square. So instead of I, you are using the value of AR square, right? So A is a nominator. If it goes to the other side of the equation, it will be in the denominator, and R, if you divide it, you can take it down the L. So the L square by R square is L by R square. What is this L by R? Basically, this is the slenderness ratio. What we were talking at the start of this topic, that slenderness ratio is very important. Now you can see that the stress, the critical stress, because P by A is the stress. So till now we were talking about critical load. Now we are talking about critical stress, which is equal to pi square E by slenderness ratio square. So sigma critical is equal to pi square E by L by R square, right? So what are these things? They are explained here. You can go through it by yourself. This is sigma critical. Mistakenly it is S, so don't get confused about it. This is sigma critical, right? Critical stress, and the rest of things are same unless this radius of gyration, which is equal to under root I by R, right? And I is equal to A into R square. The geometric ratio L by R in equation is known as slenderness ratio, this one. And what is this? It is a measure of the column's flexibility. And as we will discuss later, it serves to classify columns as long, intermediate, or short. Okay. A graph has been made for this sigma critical and L by R. You can put different values of L by R, right, to get different values of sigma critical by keeping E as constant. So this one is for structural steel. Your E is constant here, and this one is for aluminum. Your E is constant here, right? So you are just changing your L by R, and your sigma critical is changing. Okay, now you just go through this text, and you can better understand what happens. Important points are columns are long cylinder members that are subjected to axial compressive loads. The critical load is the maximum axial load that a column can support when it is on the verge of buckling. It has not started buckling, okay? This loading represents a case of neutral equilibrium. An ideal column is initially perfectly straight, made of homogeneous material, and the load is applied through the centroid of its cross section. A pin connected column will buckle about the principal axis of the cross section, having the least moment of inertia, as we already discussed. And the slenderness ratio is L by R, where R is the smallest radius of gyration of the cross section. Buckling will occur about the axis where this ratio gives the greatest value, because L will be greater. Now, solving an example on this to better understand the Euler's equation. This is A992 steel W8 by 31 member, and it is what we mentioned previously, that why we use these sections, right? Built up sections instead of the solid sections, to be used as a pin connected column. So this column is the cross section is shown here. It is a W8 by 31, and determine the largest axial load it can support before it either begins to buckle or the steel yields. So takes steel, say yielding stress is equal to 50 ksi. Now, solving from the table in appendix B of the book, they are mentioning is the mechanics of solids by Hibbeler. The column's cross-sectional area and moments of inertia are A is equal to this. Cross-sectional area for this section is 9.13 square inches. Moment of inertia in x-axis, about x-axis is 110, and about y-axis is 37.1. By inspection, buckling will occur about y-axis, right? Because this is the weakest axis, so buckling will occur about this axis. So it says y. So applying Euler's equation, we have P critical is equal to pi square EI by L square. So putting the values, your pi square, this is your E, this is your I, right? The Iy is less than Ix, so it will be a weaker axis, and divided by L square. L is your 12 feet, right? So converting it into inches, 12 into 12, so the value is 512 kips. Now your P critical is 512 kips. Okay, keeping in mind, when this load is applied, the average compressive stress in the column is at this P critical, the stress will be sigma critical will be equal to P by A, and A is 9.13. So your sigma critical or critical stress is 56.1, and your yielding stress is 50. So okay, uh, the stress exceeds the yield stress. It means the column will first yield before it buckles. The load P is determined from simple compression. For example, for this yielding, what will be the yielding load? The yielding load will be equal to the yielding stress multiplied by area. So the yielding load is 456 kip, which is less than 512 kip. So the column will not buckle first, it will first yield, and material will fail first. Okay. Now, coming to the third part of this lecture, which is effective length. To use Euler's formula for columns having different types of supports, we will modify the column length to represent the distance between the points of zero moment on the column. Right? Let me take you here. This is figure 8. The first one is pinned ends. Both the supports are pinned. Okay. So when the force is applied, the entire length of the column will subjected to buckling or bending, right? Now the second one is fixed and free ends. The one end is fixed and the other end is free. So when the load is applied, it will bend like this, but it is not complete shape, right? So you have to make it complete by assuming another part. So in this case, 2 times the length will be used in the buckling. Right here the k was 1, so k is a factor which is showing you that how much length will be effective. Le is your effective length, right? In the fixed ends, when both the ends are fixed, half of the length will be effective, it will bend. The quarter length that is attached to the support will remain straight at top and bottom, and the half of the column length at the middle, it will be working as the effective length. And when one end is fixed and the other end is pinned, so this 30% of the column length will not be supporting this or will subject to the bending or buckling, and this 70% of the length will be subjected to bending or buckling. So these are the four different conditions which depends upon the boundary conditions or the support conditions, and the effective length is different for all of them. You can get it from the K. So to use Euler's formula for columns having different types of supports, please keep in mind that it is talking about supports now. We will modify the column length to represent the distance between the points of zero moment on the column, right? Now, this distance is called the column's effective length, LE. Obviously, for a pin-ended column, LE is equal to L. For a fixed, okay, I have went through this. You please read this if you want. Now, rather than specifying the column's effective length, many design codes provide column formulas that employ a dimensionless coefficient k, called the effective length factor, just like we saw here. K is the dimensionless factor. It is a constant, right? So effective length is equal to K into L. So in this case, if L is constant for all the columns, for example, L is 10, right? So in this case, effective length will be equal to 10 into 1, 10. Here the effective length will be equal to 10 into 2, 20. So here length is 10, here length is 20, here length is 5, and here length is 7. So the effective length will be now used in the formulas. Specific value of k are also given in previous figure. Based on this generality, we can therefore write Euler's formula as P critical is equal to pi square EI divided by, now we are using KL square instead of L square, right? And you know what a K is. It is simple a constant. And also we can write it in terms of stress and the slenderness ratio. So solving another example on on the basis of what we just learned, the given data is the aluminum column in figure 9a. This is figure 9a, is braced at its top by cables, but please keep in mind that it is braced in only one direction, which is in x-axis, right? In y-axis it is free. It can buckle in this direction about x-axis, right? At the top along the x-axis, if it is assumed to be fixed at its base, it is assumed to be fixed at base and pinned and the x-axis at top. Determine the largest allowable P that can be applied. Since it cannot deflect in this shape, so this direction governs and we have to keep this direction. Use a factor of safety for buckling of 3. Take E of aluminum as 70 gigapascal, yielding stress as 215 megapascal, area as this, Ix this, and Iy this. Now buckling about x and y axis is shown in figure 9 and 9b and 9c. This is about b axis, right? Because in y in x along x axis, about x axis, sorry, it will buckle like this. This top end is free and the bottom is fixed, and in order to complete the curve we have to consider it as a double the length of the column. So in this direction the LE will be equal to 2L, which gives you 10 meter, and about y-axis it is fixed and pin, so it is 0.7 times of height, which is equal to 3.5. Okay. Now for x-axis buckling, k is equal to 2, so kl is equal to 10 meter, and for y it is 3.5. So 10 is of course obviously larger than 3.5, so that's why the equation P critical about x will be 424 kilonewton, and P critical about y in y will be about 1.31 meganewton. Please keep in mind this is meganewton, okay, which is much larger than this one. By comparison, as P is increased, the column will buckle about the x-axis. The allowable load is therefore the smaller one, because in about x-axis it is weaker, right? And this direction will govern. So P allowable will be equal to, the factor of safety was 3. We just divide this P critical by the factor of safety to get P allowable. So 424 by 3 is equal to 141 kilonewton. And to find the critical stress, just divide this critical load by the cross-sectional area, which is 56.5 megapascal. So the critical stress is less than the yielding stress. Yielding stress was 215, and therefore the Euler's equation is valid, right? Because it is not yielding, and it is the critical stress is less than the yielding stress. So the column will not yield first, it will first buckle. Okay. In the previous equation, the column was not yielding and the column was yielding before buckling, and in this case it is vice versa. In the third example, we are talking about a W6 by 15 shape, which is 24 feet long and is fixed at its ends as shown in figure 10a. Its load carrying capacity is increased by bracing it about the YY. Here it is braced about YY axis, and it is assumed to be pin connected at its mid height, right? In the mid height. Determine the load the column can support so that it does not buckle nor the material exceed the yield stress. Take E is equal to this and sigma y is this. So the buckling behavior of the column will be different about x and y axis. Now the solution starts that the buckling behavior of the column will be different about x and y axis due to bracing, right? About x axis there is no bracing, and about y axis there is a bracing. The buckled shape for each of these cases is shown in figures 10b and 10c. This is the buckled shape for about x-axis, right? Both the ends are fixed, and this is the deflected shape for about y-axis because it is braced in y direction, right? So it will buckle like this. So it is 8.4 in the y and it is 12 in the x. Okay, so the KL about x is 0.5 of 24, which is 12 feet because it is fixed at top and bottom, and in y-axis it is a half because it is braced, so it is halved, so pin and fixed, which is 0.7 of the 12, which is 8.4 feet, right? 100.8 inches, and this is 144 inches. So the moment of inertia you can also determine from the appendix. It is Ix is equal to 29.1 and Iy is 9.32. Now applying the Euler's equation, P critical x is equal to pi square EIX by KL x square. So KL in x direction is 144 and KL in y direction is 100.8. So 144 here and 100.8 here, right? And using their moment of inertia in x and y direction, so you get P critical about x is 401 and in y it is 262. So by comparison, it is evident that buckling will occur about y-axis. The area of the cross section is 4.43 square inches, so the average compressive stress in the column is P critical by A, and P critical is this one. So P critical by A is 59.3 ksi. Since this stress is less than the yield stress, so buckling will occur before the material yields. So in both the examples of example 2 and example 3, the material buckles or the column buckles before it yields, right? Now this is, I think, the last part of this video lecture, where the secant formula is also used. The Euler formula was derived assuming the load P is applied through the centroid of the column's cross-sectional area and that the column is perfectly straight. But actually this is unrealistic, since a manufactured column is never perfectly straight, nor is the application of the load known with the great accuracy. So what happens in reality? That columns never suddenly buckle, instead they begin to bend, although ever so slightly, immediately upon application of the load. As a result, the actual criterion for load application should be limited either to a specified side sway deflection of the column or by not allowing the maximum stress in the column to exceed an allowable stress, right? So this is the condition where the load is applied not at its centroid but at a distance of E. So P is applied at E, due to which the deformed shape is like this, right? And at distance x there is some uh, deflection from which is rho, right? So now the center part of the column is at a rho at a distance of rho from the original center or original point, and the load is applied at a distance p from this original point. So the total distance is this rho plus this e, right? As a result, the actual criterion for load application should be limited either to a specified sideway deflection of the column or not, by allowing the maximum stress in the column to exceed an allowable stress. Now, what is this allowable stress? To study the effect of an eccentric loading, we will apply the load P to the column at a distance as I explained you. This loading is statically equivalent to the axial load P and bending moment M is equal to PE. In both cases, and A and B are supported so that they are free to rotate. Okay. Furthermore, the xv plane is a plane of symmetry for the cross-sectional area. So this is the original condition, which is equal to this one, where you have shifted this P to this neutral axis or the centroidal axis, and you can shift it only by applying an additional moment M, which is equal to this P times E, right? So this P plus M is now applied, and when you take a cross section at this point at the distance x, so now this P and M are applied, and in addition to that, a buckling or the deflection of this point from the original axis is rho. So you have to keep this into your calculation as well. So the maximum stress in an eccentrically loaded column is caused by both the axial load and the moment. This is your axial load and this is your moment. Maximum moment occurs at the column's midpoint, and it has a magnitude of m is equal to p into c, as I told you, E plus rho maximum. And m is equal to, this is the derived form, pe into secant of under root p by ei into L by 2, because L by 2 is the middle of the column. As shown in figure 12b, this is your figure 12b. These stresses are due to the axial stresses, these are due to bending stresses, just add them, and these are your resultant stresses. So sigma max is equal to P by A is axial stresses plus MC by I are the flexural stresses. And sigma max is equal to, when you put the value of M is equal to P into E. So you are replacing M with P into E into C by I secant of this value, right? You are just putting M here with this additional C. So since the radius of gyration is R is equal to under root I by A, the above equation can also be written in the form called the secant formula. So you can write it as a, if you put uh, this I as a A into R square, so P by A and P by A can be taken as common, so 1 will be left here, and plus EC by R square here, and secant of this thing. So this is your secant formula, where you consider the eccentricity as well as the radius of gyration as well as the distance of the distance from the neutral axis to the point where you are considering to find the stresses. The effective length and all the details are including in this secant formula. These are the terminologies that are used in the equation. Important points are, due to imperfection in manufacturing or specific application of the load, a column will never suddenly buckle. Instead, it begins to bend as it is loaded. So the load applied to a column is related to its deflection in a non-linear manner, and so the principle of superposition does not apply. As the slenderness ratio increases, eccentrically loaded columns tend to fail at or near the Euler buckling load. Okay. Another example, we are going to solve it on this secant formula. The given data is a W8 by 40 A992 steel column shown in figure 13a is fixed at its base. It is fixed in the base at the top so that it is fixed from displacement, yet free to rotate about y axis. Okay, in about y axis it is free to rotate, but the displacement is fixed. Also, it can sway to the side in the YZ plane, and it can sway in the YZ plane as well. Determine the maximum eccentric load. Now the load is applied at 9 inches from this line, right? The centroid, it is applied at 9 inches. Support before it either begins to buckle or the steel yields, and the yield stress is 50 ksi. Now from the support condition, it is seen that about the y axis the column behaves as if it were pinned at its top and fixed at its bottom. and subjected to an axial load P. So in figure 13b, you can see the deformed shape about the y-axis. So its effective length is like fixed and pin, and effective length is 8.4. However, about x-axis, it is just like the free end, right? So mm, about the x-axis, the column is free at the top, just like I said, and fixed at the bottom, so the length will be double. Now, why y-axis buckling is from figure 13d, it can be seen that the effective length factor is zero point 0.7, right? It is not D, I think it is B. Please make it B, right? So KLY is equal to zero point 0.7 of 12, which is 8.4, just like I described previously. And uh, knowing all the other details, for example ix and iy, so putting the values in the Euler's equation, which is pi square ei by kl square, the critical load is 1383 kips. Now, for the x-axis buckling, the kx is equal to 2, so the effective length will be 24, the double of the original length. And we know the other details, putting that in the formula. Why we are applying the secant formula here? Because it mentioned in its statement that it can deform in the about the x-axis. So that's why in about y-axis, it was only the Euler formula that was governing, but about x-axis we can use the secant formula because the buckling is here, and also the eccentricity is from the x-axis, if you can see, right? Therefore we are using the secant formula about the x-axis. So putting all the details in this formula, and we get the value of px, which is equal to 115 gibbs. Since this value is less than p critical, which was 1383, right? Therefore failure will occur about the x-axis. And that's all from my side. And if you have any question, please mention so that I will answer that for you. And if you have any suggestions, please also mention. Thank you very much.